Hello everybody and welcome to the 14th lecture of MHM 427AT MUA 782. We are going to start this lecture with solving one example to just review what we learned during the last week. It's like question 14.38 of your textbook. Consider a carbonated drink like Coca-Cola, like Pepsi, or other sodas that you drink in a bottle at 37 degrees and 130 kilopascal. So it's normally is not that warm because you drink it from the refrigerator. Was cold, but just like consider like that. Assuming the gas space above the liquid consists of a saturated mixture of carbon dioxide and water vapor and treating the drink as water. Determine A, the mole fraction of the water vapor in carbon dioxide gas, and B, the mass of dissolved carbon dioxide in a 200 milliliter drink. Okay, so what do you think? What should be our first step? So just first look at the assumption. First, is saying that the liquid drink can be treated as water. Okay. What other assumption we can make? I think it's a very good assumption if I can say that both carbon dioxide and water vapor can be considered as ideal gases. What else? We can also say that the carbon dioxide gas and water vapor in the bottle are saturated. What else? Is there anything else that we can say? Yeah, we can also say that the carbon dioxide is weakly soluble in water, so we can use the Henry's law. Okay, so now we have all those assumptions. Let's start. So the saturation pressure of water, so let me write it, saturation pressure of water Why? Because we said that we can it's like drink, we consider it as water. So saturation pressure of water at 37, this temperature, we need that one, so we go to table A9 and we read it, that saturation pressure of water at 37 Celsius is 6.33 kilopascal. We also said that because carbon dioxide is weakly soluble in water, we can apply the Henry's law, or find the to do that, first we need to find the Henry's constant. So Henry's constant, let me write it down here. Henry's constant. How you need to find it? You need to go to table 14.6, and for carbon dioxide solved in water at 37 degrees, which is 310 Kelvin, H is equal to 2117 bar. Okay, what else we can read from the tables? Molar mass, so molar mass of carbon dioxide and molar mass of water, we can read it from the table, or it's like something that we know, but we can go to table A1 and read them. So for carbon dioxide, CO2 is 44 kilogram kilomole, and for water 2 is 18 kilogram kilomole. Okay, that's there are some like information that based on the assumptions we went and we read from the tables. Now let's get into it and start analyzing and solving. Okay, we just mentioned that carbon dioxide in a bottle is saturated. Okay, so how we can find the partial pressure of water vapor in the air? So basically the partial pressure of water vapor in the air is simply the saturation pressure of water at 37. So we easily can say that P vapor, because we said that it's saturated, is like saturated at water at 37 degrees. Do we have it? Yes, here if you see we went to the table and we read it, so we just write it down. It's 6.33 kilopascal. Assuming both carbon dioxide and vapor to be ideal gases, so the mole fraction of water, or mole fraction or molar fraction of water vapor in the carbon dioxide gas, we can find it like this: vapor is equal to that P vapor divided by P total. Okay, so it's 6.33 kilopascal. What is P total? Is given here 130 kilopascal. So divided by 130 kilopascal is equal to 0.0487. So 0 is a very small number, 4.9%. Okay. What was it? It was exactly what is asking here. You see that the A is asking us to find the mole fraction of water. So simply mole fraction of water vapor. So simply we could find it, and it's equal to 4.9%. Now we need to go and find section B. Let me just like put it here, A. But let's go back to the question and see what the section B is asking us. The section B is asking the mass of dissolved carbon dioxide in a 200 milliliter drink. Okay, so it means that finally we need to find something in gram or kilogram, because it's like a dissolved is asking the mass of dissolved carbon dioxide. Okay, so what do you think what we should do first to find that the dissolved the mass, or like a gram of carbon dioxide which is dissolved in the water or drink? So I think that if I don't know what do you think, but I think the best would be first sorry, I don't know why it's, but I think first we need to find the mass fraction of dissolved carbon dioxide, and after that, if we multiply the mass fraction of dissolved carbon dioxide multiply by the weight of the drink, we can have the mass of dissolved carbon dioxide. Okay, so it's better first to focus on finding the mass fraction of dissolved carbon dioxide in liquid water or drink. To do that, first we need to find the partial pressure of carbon dioxide. So the partial pressure of CO2 gas is P minus P vapor will be 30 kilopascal minus 6.33 kilopascal. So basically this is 123.7 kilopascal. From this one we can find from this, because we have the partial pressure of carbon dioxide, now we can apply the Henry's law. So if you remember, Henry's law was saying that the mole fraction of gas but on the liquid side will be equal to partial pressure of the gas on the gas side divided by a constant that we find it. If you remember, just like we mentioned about the H or Henry's constant that we went to the table 14.6 and we read it, so we have it here is equal to 2170 bar. Here is we have the partial pressure of carbon dioxide, so we just write it down, is equal to 123.7 kilopascal. Okay, so we just do the calculation and we have the mole fraction of carbon dioxide. So if you do that, like lots of students do the same, and you lose lots of mark. Why? Because we can't divide kilopascal to bar. If you remember, the Henry's constant is based on bar. That's very important, because it's like lots of students I've seen during the last couple of years that make a mistake here. Okay, so then first we need to change this one to bar. Okay, so we can say that, okay, 123.7 kilopascal is more or less is equal to 1.237 bar. So then the mole fraction of carbon dioxide in the drink can be liquid side, let me just write it down, is 1.237 bar divided by 2170 bar, which is equal to 5.7 10 to the power of minus 4. Okay, now we find this one from this mole fraction of carbon dioxide in the drink. We can find the mole fraction of water in the drink simply just by 1 minus this number. So the mole fraction of water in a drink, liquid side, because it can't be more than 1, so it's 1 minus 5.7 10 to the power of minus 4 will be equal to 0.9994. Okay, so now we have the mole fraction of water in the drink. What we need to do is we need to find the mass and mole fraction of mixture. Okay, because what we have is a mixture of carbon dioxide and water. Okay, so let's open another page and try to find that, the mixture. Okay, for mixture, if you remember, we said that the mixture is equal to YIMI. Okay, it's very simple. So Y of liquid water molar weight of water plus Y of carbon dioxide liquids multiplied by carbon dioxide. So the mass of mixture will be 0.9994 multiplied by 18 kilogram kilomole plus 5.7 10 to the power of minus 4 multiplied by 44 kilogram kilomole. What we are going to have is 18 kilogram kilomole. It will be very little, but it's not always like that, okay? So please calculate it, don't just like put it and make sure that you all the time will be the same situation. At the same time, during the final exam, it is the same story. If you don't calculate the molar mass of the mixture, even though the number is close, you can't claim that, okay, I didn't calculate, but my number is 18 is the same as water, so why I didn't get any mark? No, because you missed the very important step, even though the final answer is very close, but you need to calculate it. Okay, so now we have the molar mass of mixture. So how we are going to find the mass fraction of dissolved carbon dioxide? Because if you remember, we said that we need to find the W of carbon dioxide on the liquid side, and when we find this one, after that we can have the what the question is asking, which is the mass of dissolved carbon dioxide in 200 milliliter of drink. So first then we need to find this mass fraction of dissolved carbon dioxide. Okay, it's very simple. I'm just like going to write it down. You remember that we said there is a correlation that we can relate mass and mole fraction of mixture. So if you remember, was I m. Here is mixture. So carbon dioxide liquid side is equal to mole fraction of carbon dioxide liquid side carbon dioxide molar weight and mixture. So then we will have liquid side is equal to 5.7 10 to the power of minus 4 44 kilogram kilomole divided by 18 kilogram kilomole will be equal to 0.00139. Okay, so now we have it. Easily we can say that carbon dioxide is equal to m. But how about this m? So because we considered drink as a water, so 200 milliliter of water, we are with a very good assumption, we can say that is equal to 200 grams. So 0.00139 multiply by 200 gram, what we have will be 0.278 gram of dissolved carbon dioxide in this drink. Okay, so it's not very complicated, but it's a little bit tricky, so you need to start with the right assumption, and after that you continue and step by step. Okay, now let's start talking about steady mass diffusion through a wall. Many practical mass transfer problems involve the diffusion of a species through a plain parallel medium that does not involve any chemical reaction under one-dimension steady condition, the same as that we are showing here. Look at this. Look at this figure and consider a solid plane wall with area A, with the thickness of L and density of rho, which is constant. The wall subjected on both sides to different concentrations. The boundary surfaces at x equal to 0 and x equal to L are located within the solid adjacent to the interfaces, and mass fractions at those surfaces are given to be WA1 and WA2. The mass fraction of species in the wall varies in x direction and can be expressed as WAX. Am I right? Is it like a you remember for conduction we had like a temperature profile, how the temperature would change from the right hand side to the left hand side? More or less the same thing. We are going to have a like a function, like a concentration distribution function basically. So for steady one-dimensional, no chemical reaction mass transfer through a wall, concentration does not change with the time. As you can see, it's just like a linear from WA1 to WA2. But again, think about the assumption: steady, one-dimensional, no chemical reactions. So based on conservation of mass, so then we can say that m dot diffusion on A is equal to A, and is constant. Okay, but what we have is steady, one-dimensional, no chemical reaction. So we have this one. You remember how we could calculate the JI Fick's law? I is equal to minus rho DAB dWA dx. So basically then m dot diffusion on A divided by A is equal, because this A can go the other side and the other side can stay just JA minus rho DAB dWA dx. Okay, so let's just open another page and continue that. Let me just write it down one more time, and after that we can continue from that. So m dot if A divided by A from the Fick's law is rho DAB WA dx. So we can solve it, but of course the boundary condition at x 0 is WA1 and x equal to L, WL is equal to WA2. So basically this can come out of the integration. So df a divided by a 0 to L dx is equal to minus WA1 to WA2 rho dAB dWA. Okay, so basically this one will be m dot if a and vol is equal to rho dAB A1 minus A2, sorry, WA2 divided by L. L came from here, and after that we put it that the other side. Okay, this one, is there any way that we can do anything about it? Because we have rho dAB. Sorry, I forgot A here. Because A comes from here. Then, okay. So let me open another page. So we got to this point that m dot diffusion A through the vol is equal to rho dAB A WA1 minus WA2 divided by L. So easily we know that it will be equal to dAB A rho A1 minus rho A2 divided by L. Okay. But as I mentioned, is again we know that is steady, one-dimensional, no chemical reaction. It's very look like to what we did for conduction heat transfer in like a one-dimensional conduction heat transfer, if you remember. And the same as heat transfer, if you remember, we used the concept of electrical engineering and resistance, and we just like related it somehow to heat transfer. We can do the same thing to diffusion resistance as well. Instead of heat transfer, we can do it for mass transfer. You can see here for heat transfer we said that basically for all of them we have a driving force divided by a resisting force. In heat transfer the driving force is temperature difference, and we have R here, the mass, the m dot diffusion is important for us, and the driving force is difference in concentration, different format of expressing it, divided by R mass, which is the diffusion resistance. Okay, but now how we find the diffusion resistance? So if we want to find the diffusion resistance, we just go back here and write it down, and we try to see if we can find the diffusion resistance. So m dot diffusion, we find that it's like rho d ABA WA1 minus WA2 divided by L. So if we compare that one with this one, this looks the same. this looks the same. I through the wall. So basically R, or diffusion resistance, mass, is equal to L divided by rho dAB A. Okay, and we call it diffusion resistance. Sometimes in some textbook they show it with R mass. Sometimes we can just like simply write it as R diffusion, or R diffusion through the wall. We can also define, if you recall, we mentioned that concentration can be shown in two different ways of mass base and molar base. This is, of course, is mass base. For the molar base or molar diffusion resistance, we show it these are mass, or R bar, diff and wall. When there is a bar on the R, we call it molar diffusion resistance, and will be equal to L divided by C dAB. It's just like different representation of concentration, as we discussed it before, mass base and molar base. But when we do the molar base, so we are not talking about mass anymore. What we are talking about N. So basically will be equal to YA1 minus YA2 divided by R mass. Just like, don't confuse yourself. It's very simple concept, just like different representation or different way of showing the same thing. It's basically we are saying the same thing is two different languages, in English or French basically. But let me just write it a little bit neater for you to get. So for mass base, we mentioned that m dot is important for us, so diffusion A through the wall. We said that if we write it through the driving force divided by resisting force, we can say that like minus A2 L rho dAB A, and we said that we call this one R mass or R diffusion wall. And if we want to use the molar base, of course we are not talking about M anymore, we are talking about N diffusion A through the wall, which is equal to molar fraction divided by LCDAB, that we call this one R bar mass or R bar diffusion wall, which is molar diffusion resistance. Both of these correlations can be used to determine the diffusion rate of a species A across the wall, depending whether the mass or molar fractions are known at the boundaries. So it's based on the boundary and what kind of information we have. We can go either way with the mass base or molar base. There is no particular difference actually between these two. The only thing is it's just like different representation of same thing. But we just like talked about to parallel or wall. How about a steady one-dimensional non-reacting mass transfer through cylindrical and spherical layers? There is another way to express why one-dimensional mass diffusion through a wall if it's involved a gas. Let me just like show it here. You see that, for example, if we are dealing with a cylindrical coordinate, basically again we are speaking about what is important for us is m dot diffusion, driving force divided by resisting force, and for the same thing but again different representation based on the molar base, we are talking about n dot driving force, which is the difference between molar fraction divided by resisting force, which if you remember we just talked about this too, so it's not a like a diffusion resistance, molar diffusion resistance. If you go to your textbook you can find all those correlations, so you don't need to have them in your mind or save them anywhere. It's like the exam is open book. You can just go to your textbook and use the correlations, so don't worry about it if it looks a little bit complicated. For spherical coordinates, or like a one-dimensional non-reacting mass transfer, again all those things again steady one-dimensional but in different coordination, again for when we are speaking about the mass base, what is important for us is m dot driving force mass fractions divided by resisting force, and if we want to use the molar base, so the important thing for us is n dot diffusion. The driving force will be mole fraction, and resisting force will be molar diffusion resistance. Okay, so we are not going to spend more time about it. But look at here, it's like there is I told you that the concentration of the gas species in a solid at the interface is proportional to partial pressure of the adjacent gas and can be expressed as if you remember, Ca solid side is equal to AB P A gas side. What was it? It was solubility. You remember we talked about it, so it's kilomole bar is the unit, but solubility of what? Solubility of gas A in the solid B. That's the reason we say that AB, the solubility of gas A in solid B. I also mentioned that the product of solubility and diffusion coefficient is called permeability. So if we show it like this, we multiply by DAB. So Solubility multiplied by diffusion coefficient is called permeability, and the unit of permeability is kilomole m.s.bar. Okay, we talked about it, but just I'm mentioning it one more time to review it. So let's try to see what we can do with this this picture, and if we can do anything with it. So the molar flow rate of, let me just bring this picture to this side and make it a little bit, because it's very busy, the other one. Okay, so the molar flow rate of a gas through a solid under a steady one-dimensional non-reacting condition again can be expressed in another way as well. We talked one way, but let's can define it as diff A and vol is equal to dAb A C A1 minus C A2 divided by L. Okay, so, and if you remember, we also said that CA1 is equal to ABP A1, the partial pressure of A, and the 2 is AB, partial pressure of A2. Okay, if we apply those into the correlation, what we are going to have is we are going to have that n dot diffusion A vol, the vol is equal to dAb A. I'm just like replacing CA A1 and CA2 with the solvability multiplied by the partial pressure. AB P1 minus solvability PA2 divided by L. We know that solvability is constant, so can come the other side as well, so it's dAb solvability AB A PA1 minus partial pressure of 2 divided by L. This we just like talked about it. Solvability multiplied by we just talked about the diffusion coefficient. So how we call it? We call it permeability. What unit has is kilomole, or so, and dot diffusion A vol basically is equal to permeability AB A partial pressure of 1 PA2 divided by L. So PA1 and PA2 are the partial pressure of the gas A on the two sides of the wall. Okay, so for an ideal gas at a standard condition of, let's say, at a standard condition, the occupied volume is around, if I'm not mistaken, let me just open another page and write it down. So for an ideal gas, if we have ideal gas at a standard condition, the occupied volume is equal to 22.414 cubic meter. And the volume flow rate of the gas through the wall by diffusion can be determined as I diffusion and A is equal to 22.414 n dot diffusion and A. How that came, it's from V is equal to dot A RUT, because we are speaking about the ideal gas. So just keep that in mind as well. So sometimes the rule of like ideal gas can help us to be able to solve an example. But let's see how we can put all those information that we received today into practice and solving one example. So let's solve 14.51 of your textbook. A thin plastic membrane separates hydrogen from air. The molar concentration of hydrogen in the membrane at the inner and outer surfaces are given. The binary diffusion coefficient of hydrogen is given. Determine the mass flow rate of hydrogen by diffusion through the membrane under a steady condition if the thickness of membrane is A 2 millimeter and the B 0.5 millimeter. So basically everything is the same, the only thing that is changing is L. Okay, am I right? So what am I saying? Everything is clear. What we have, what is clear? DAB, we have it. Yes, it's given. What is it? 5.3, 10 to the power of minus 10. What else we have? CA1, we have it, is given 0.045. And we also have CA2, which is 0.002. Okay. Yeah, it's a molar concentration of the hydrogen in membrane. So we have those two. Basically, all the information is provided. Diffusion is equal to N dot diffusion divided by A is equal to DAB CA1 minus CA2 divided by L. Okay, so then we have 5.3, 10 to the power of minus 10, 2 divided by 0.045 minus 0.002 kilomole divided by, first we are speaking about the A section where L is 2 millimeter. So in that case, J diffusion is equal to 1.14, 10 to the power of minus 8 kilomole. But it's not what the question is asking. The question is asking determine the mass flow rate. So it wants us the mass flow rate in two different conditions. So we know that the mass flow rate m dot diffusion is equal to m diffusion, the molar, so 2 kilomole. What is this 2 came from? What we are talking about? Hydrogen. So we go to the table, if you can't remember from your heart, so we go to the table and we read the molar mass of hydrogen, multiply by 1.14, we just like calculated 10 to the power of minus 8 kilomole to S, this goes, so basically what we have is m dot diffusion will be equal to 2.28 10 to the power of minus 8 gram s second. Okay, looks nice, very simple. We find section A. Section B is saying that basically do everything the same, just change the L, if you remember, in two different conditions, just the thickness of the membrane. So for B, when the membrane the L is 0.5 meter, so if we do exactly the same thing, m dot should be equal to 9.12 10 to the power of minus 8 gram. Okay, so basically that's it. Try to do the second section at home and see if you are you can get the same number, but basically it's just it's very simple. Everything is exactly the same. The only thing that we changed was the thickness of the membrane. The other story that we might see in a daily life is about the houses, the roof, and all those stories, the concrete. So let's see if we can solve this this question as well. The roof of a house the size is given. It's made of 20 centimeter thick concrete layer. Interior of the house is maintained at temperature is given, 50% relative humidity, local atmosphere pressure is given, and is asking determine the amount of water vapor that will migrate through the roof in 24 hours if the average outside condition during that period are 3 centigrade and 30% relative humidity. Basically during the winter, the permeability of the concrete to water vapor is also given. So basically it's like what is asking is we have a concrete layer and we have another layer which is it's vapor retarder. This moisture goes through. Here we have it's 20 centimeter. Inside is 25 degrees. Relative humidity is 50%. On the other side, the temperature is 3. Relative humidity is 30, and it's 100 kilopascal. Okay. I don't know if we can solve that one, because it looks to me that we are a little bit missing some kind of information. Why? Because now we are dealing with two different layers, so we don't know how we are going to calculate the R total. So let's wait here and talk about the water vapor migration in building, because we have a section for it in our textbook, but we wanted to solve it, but after that we realized that we don't have enough information. Okay, let's go back and try to just a little bit speak about the concept, and we come back to this question. Okay, so basically we can say that m dot E, the vapor is A delta P vapor RV total. Basically it's simply we can say that, and we also can rewrite it as a permeability per EA ability, the pressure, partial pressure divided by L. So the permeability of most construction materials is usually expressed for a given thickness instead of per unit thickness, and it's called permanence. Okay, so we need to keep that in mind as well. So it's M, which is like permeability divided by L. We call it permanence. Permanence. So the permeability of the most construction material is normally it's based on the unit of the thickness. Okay, so we call it permanence. Don't mix those things. Then easily we can say that this is permanence. This is permanence. Okay, so we can show it like that. But in this case, if we want to show it in terms of like a driving force and resisting force, how we are going to show it? So it will be sorry, let me just so this is basically is the vapor resistance, and it's equal to 1 divided by permanence. And permanence itself is permeability divided by L, and the unit of permanence is gram s square meter Pascal. Okay, so now we find the vapor resistance. So when we go here, now we have the vapor resistance, the resistance of material, we know it, and we can solve the problem. So now let's go back to the this question and try to solve it. I'm going just like to take it again to the new page, open a new page to make it easier for us to follow. Okay, now we have this one. Sorry. Okay, let's start, because now we find it how we can calculate the resistance of the vapor. We know how to calculate the resistance of roof, so we are basically fine. What we are going to we need to find the amount of vapor, water vapor that will migrate through the roof. So basically is asking us not m dot, the m of vapor in 24 hours. To do that, to find that, what we need to do is we need to find m dot and multiply it by delta T, which is 24 hours multiplied by 360 seconds. Okay, so again the first step is finding m dot of water vapor. So m dot vapor A P1 minus P2, but instead of R here, what we have is R total. What is R total? As we said, is vapor roof plus vapor film. Okay, so now let's, for our film, we just like said that it's 1 divided by permanence, and for our roof we said that is L divided by P. Is it a P or what is it? It's permanence basically. So L divided by permanence plus 1 divided by L divided by permeability plus 1 divided by permanence. So let's open another page and calculate these ones. Okay, let me write it down. So our total is L permeability plus 1 divided by permanence. Do we have the L? Yes, for concrete we have 0.2 meters. How about the permeability of concrete? Do we have it? Let's go and check if we have it. The permeability of concrete is given, so we just like write it down, 24.7 10 to the power of minus 12 milligram SMPa plus 1 divided by 26 multiplied by 10 to the power of minus 12 kilogram SM2 Pascal. So basically our total can be found. Our total is equal to 4.656 10 to the power of 10 M2 Pascal divided by kg. But you might ask that, okay, where did you find this number? Go to your textbook and see if you can find this number through any kind of like a table, and see if like is there any table, anything that you can read it from there, because when I check here I don't see any number like 26 multiplied by 10 to the power of minus 12, but most probably it should be somewhere, I don't know, from a table or something. Go and check your textbook and see if you can find that number. So our total, we can find it. Now m dot v, we know that it's equal to a minus p 2 divided by our total, and it will be equal to a partial sat 1 minus phi p sat 2 divided by our total. Surface area, do we have it? Yes, it's given 15 multiplied by 8 square meter. How about the phi1 and phi1 and phi2? We just like go to the question and we see if we can find it. Yes, relative humidity, we have it 50%, 30%. So 50% is 0.5, 30% is 0.3. The saturation pressure 0.1. How we can find it? How we can find that one? So of course we have the temperature. We go to the table 14.9 and we read the pressure at 3 degrees. The saturation pressure is 768 Pascal, and at 25 degrees the saturation pressure is 3169 Pascal. So we just put those into the equation. We calculated our total. We have A, so basically m dot v. Okay, there is no space. Let me open another page and write it down. Okay, so m dot v will be equal to 3.49 10 to the power of minus 6 kilogram per second. Okay, now we have it. Try to see if you can get to the same number, and but it's our job is not done. Why? Because it's asking determine the amount of water vapor that will migrate through the roof in one day. So basically it's asking us to find the m of vapor 24 hours. So m dot v multiplied by 24 3 second, so 3.49 10 to the power of minus 6 kilogram per second multiplied by 24 multiplied by 3600 seconds. So what we have is 0.302 kilogram or 302 gram. Okay, that's did you see? It was very easy to find, but the only thing you need to do is to go and see how we find that one, the permanence, and the table. There is like a table in your textbook that we read it from that table. The rest was very easy. We followed the same kind of like a concept of heat transfer. We find our total, and after that we put it into the correlation driving force divided by resisting force, and we found m dot v. After that, when we have m dot v, if we multiply it by the time, we can have the amount of moisture that migrates or flows through the roof, and we calculated that, and that was 302 grams. Okay, please try it at home to see if you can get the same number and same results. I think that's it for today, and we are going to continue to talk about mass transfer in our next session.